30% of people with epilepsy have tried every drug available. None of them work. That gap between sensing and preventing is what a new class of brain sensor is designed to help close. The device is an organic electrochemical transistor array, OECT. It sits inside the cortex, reading glutamate and GABA simultaneously, the brain's accelerator and brake. Working prototypes have held 7 to 21 days of stable recording inside a living brain. That's 5 to 10 times longer than the carbon fiber sensor benchmarks set between 2018 and 2022. Detecting GABA required a 2-enzyme cascade that has proven extremely difficult to stabilize on an electrode. An enzyme half-life in vivo remains the field's primary rate-limiting challenge. George Maliaras at Cambridge's Department of Bioelectronics is among the key figures. PEDOT, PSS, a soft, ion-conducting polymer, amplifies chemical signals with transconductance that can exceed 10 millisiemens, orders of magnitude above comparable silicon devices. The dual sensor works like noise-canceling headphones applied to molecular biology. One pixel detects glutamate alone. A neighboring pixel runs the GABA cascade. The difference is net inhibition. Neuropsychiatric drug trials fail at roughly 89%, among the worst rates of any disease category. One contributing factor researchers cite, the inability to confirm whether a drug is actually hitting its intended neurochemical target in a living brain. Closed-loop neurostimulators already exist. Medtronic's deep brain stimulators, NeuroPace's RNS system. What they currently lack is real-time molecular feedback. That's the gap this platform is designed to fill, if it clears the remaining technical hurdles. Analyst estimates place global investment in OECT neural interfaces at $380 to $520 million annually in 2025 and 2026, though the direct research funding tracked for this specific platform is far more modest. First-in-human closed-loop EI stimulation for treatment-resistant epilepsy is one scenario researchers consider plausible by around 2028, contingent on successful primate replication and solving the unsolved problem of in vivo recalibration without removing the device. One honest flag researchers themselves raise, a device that reads excitatory-inhibitory balance in real time can also read cognitive state, stress, decision-making precursors.